These are examples of how to solve problems involving work, power, and energy. Work is the product of force in newtons and distance in meters, and the symbols are as follows: W for work, capital F for force, and D for distance. So for problem 28, the work done is a force of 5 newtons multiplied by 1.2 meters, and you end up with 6 newton meters. And since newton meter is joules, this is also 6 joules. We repeat it for problem 29, 2 newtons times 1.2 meters to give us 2.4 joules. Number 30, 20 newtons times 3.5 meters to end up with 70 joules. And for problem 31, 500 newtons times 2.2 meters to end up with 1,100 joules. The gain of potential energy when we lift the barbell to this height is the same as the work done. So we calculated for 1100 joules for work done, and that is the same as the gain of potential energy. Power is work divided by time, where work is in joules and time is in seconds. Also, joules per second is equivalent to watts. So for problem 32, we divide the work done of 100 joules by 2 seconds, which is the time, to end up with 50 joules per second or 50 watts. For problem 33, power, which is work over time, we first have to calculate for work done, which is force times distance. So we multiply 500 newtons of force by a distance of 2.2 meters, and the answer to that divide by the time of 1.4 seconds. So this is 1100 joules divided by 1.4 seconds, or 785.7 joules per second, which can also be written as 786 watts. We can also express the power in terms of horsepower. Since 746 watts is 1 horsepower, we can use this conversion factor, 786 watts multiplied by 1 horsepower per 746 watts, and the unit watts gets canceled out here. We end up with 1.05 horsepower. The gravitational potential energy is equal to the product of weight and height. The symbol for it is PE, and weight is mass m times g, which is gravitational acceleration, and h here is height. So for problem 34, we have a book that has a mass of 3 kilograms. It's lifted to a height of 2 meters, and the increase in gravitational potential energy is 60 joules. So we're asked to show that. So let's see here the calculation: GPE equals mgh, mass of 3 kilograms, gravitational acceleration, which is 9.8 meters per second squared, is rounded to 10. So multiply it again by height of 2 meters, and we have 16 newton meters. A newton meter is the same as joules, so the gravitational potential energy is 60 joules. For problem 35, we're asked to show that the gravitational potential energy of a 1,000 kilogram boulder raised 5 meters above the ground level is 50,000 joules. So our working equation is GPE equals mgh. Our mass is 1,000 kilograms. Our gravitational acceleration is 10 meters per second squared, and our height is 5 meters. So this gives us 50,000 newton meters, or 50,000 joules. You'll wonder where the unit newton came from. When you combine kilogram and meter per second squared, that is equivalent to a newton. Although we express gravitational acceleration typically in units of meter per second squared, you can see that by dimensional analysis, the unit can also be newton per kilogram. The kinetic energy of an object is equal to the product of 1/2 times mass times the square of the speed. So this translates to the following symbols. Ke equals 1 half mv squared. Your mass has to be in kilograms and your speed or velocity has to be in meters per seconds. So for problem 36, our mass is 1 kilogram and the speed is 3 meters per second. We're asked to show that the kinetic energy is 4.5 joules. So kinetic energy is 1 half times a mass of 1 kilograms times the speed of 3 meters per second. And we square that. So this ends up as zero point 0.5 times 1 times 9. And that gives you 4.5 joules. We do the same thing for problem 37, where our mass is 84 kilograms and it's moving at a speed or velocity of 10 meters per second. So again, applying the formula, 1 half of mass of 84 kilograms multiplied by the quantity 10 meters per second squared. So this is zero point 0.5 times 84 times 100, and that gives you 4,200 joules. The work energy theorem tells us that the work done on an object is equal to the change in the kinetic energy. So for problem 38, we're asked to show that 24 joules of work is done when a 3 kilogram block of ice is moved from rest to a speed of 4 meters per second. So this 3 kilograms is our mass. It starts from rest, so our initial velocity is zero, and therefore 4 meters per second is our final velocity. So here is our working equation. W, or work, is change in kinetic energy, and that is final kinetic energy minus initial kinetic energy. Recall that kinetic energy is 1 half mv squared. So if you're looking for final kinetic energy, you need to use the final velocity. Similarly, if you need to get initial kinetic energy, you need to use the initial velocity. So this again translates to zero point 0.5 m times the quantity final velocity squared minus zero point 0.5 m times the quantity initial velocity squared. So I wrote here the object started from rest, your initial velocity is zero, and therefore your initial kinetic energy is zero. Therefore, if you look at this equation, we're down to work done is simply the final kinetic energy of the object, which is zero point 0.5 times mass times the square of your final velocity. Substituting our values, we have zero point 0.5 times a mass of 3 kilograms times the velocity final of 4 meters per second, and we square that, and we end up with 24 joules. For problem 39, we are asked to show that a 2,500,000 joules change in kinetic energy occurs for an airplane that is moved 500 meters in takeoff by a sustained force of 5,000 newtons. So here's our working equation. Work is equal to change in kinetic energy, but work is also equivalent to the product of force times distance. So the force applied here is 5,000 newtons and the distance moved is 500 meters. So our work done is 25 million, I'm sorry, 2,500,000 joules. And the work done is the same as the change in kinetic energy, so the change in kinetic energy is the same value.